Good afternoon, everybody. Welcome to Thursday afternoon of Chem 170 with your host, me, Dr. White. And I'd like to say this semester, you people have treated me really well. I mean, really well. And because of that, I'd like to thank you. The way I'll thank you is take Monday off. We'll just not have a lecture on Monday. And if you have any other classes at ECC, take them off. Tell them Dr. White said it's the 4th of July and we will not have any lectures on Monday, but we will on Tuesday. So now, important, don't forget, today after class, after a couple minutes, I will send out an email with the password for test number 2. Was that hot and good? But test number 2, you'll have until tomorrow, 11 a.m. Friday, July 1st. Where did this year go? It's more than half done. Wow. Anyways, you'll have until tomorrow, 11 a.m. to upload your answer for test number 2 to D2L. I have it already ready for you to download in D2L. Last night I checked, and oh no, I forgot to make it visible. It's visible now, I just checked. And that's test number 2. I promise by Sunday, 1 p.m., if not earlier, I will grade test number 2. I will post your overall score in D2L for test number 2. And by Sunday, 1 p.m., if not earlier, I will send out individual emails for each person with your each points you get, how many points you got for each answer on test 2. I guarantee it by Sunday, 1 p.m. Should be sometime, probably Saturday. When I do that, I will post an announcement in D2L and send out an email to all of you that it's there and available. All right, let's get back to esters. And where were we on esters? Well, if I remember correctly, and hopefully I do, sometimes I don't. We're talking about saponification of an ester. And that's where you take an ester, carbonyl with an R group and OR. Remember, carbonyl, carbon, double bond to oxygen. Watered base, and for this class, I'll just stick to sodium hydroxide. And you get a carboxylate anion of the carboxylic acid you would have used to make that ester, plus the alcohol you would have used to make that ester. So let's have some fun with it. I'll do one, then I'm going to let you have fun. And sometimes I'll write it like this. And the question is, what's the product or products? And on test, I do this. Sometimes I forget the question marks. Remember that. Sometimes I forget the question marks, but I'll always have a plus there that tells you there are 2 products. So how do we do this? We look at the starting material and we say, what's different? Hi, Hannah. Well, she's not in yet. But anyways, what's there? Ooh, a carbonyl, carbon double bond to oxygen. And now that you're in, hi, Hannah. But anyways, oxygen. On the oxygen, I have carbons. I'm going to call R prime. On the carbonyl carbon, carbon double bond oxygen, I'll call those carbons right here R. So this is my R. This is my R prime. When you react that with base and water, NaOH is a base, what you get is not the carboxylic acid, because you're in base, that becomes the carboxylate anion of the carboxylic acid you would have used to make that ester, but you get also the alcohol you would have used to make that ester. Remember, the carbon with the oxygen here is the carbon in R prime with the hydroxyl group. So let me make some room here. We're getting two products. First one, R is CH3, CH2, carbonyl, O minus. You don't have to put the charges, but I will. And then plus that carboxylate anion of the carboxylic acid you would have used to make that ester. And then the alcohol, what's our prime? 3 carbons. Notice the uncarbon is bonded to this oxygen. So I'll have, let me move us over. Three carbons, and carbon has the hydroxyl group, that alcohol. Now, Hannah, you came in a little late. I told everybody, don't forget, after class and lab today, I will be sending out the email with the password for test number 2. You have until 11 a.m. tomorrow to take it and upload it. I think I said take an hour and a half. If you need a few more minutes, it should take you only about 45 minutes to be done to practice problems, maybe even 40. And don't forget to do that. And don't forget, Monday is July 4th, so we won't have any class. All right, I better share the fun. And what would be the 2 products you'd get if you react that molecule with sodium hydroxide and water? It's your turn to have some fun. When you're done, you want to try the thumbs up method? Thank you, Jordan. And remember, be patient. Let's wait for everybody to finish. Thank you, Jimmy. Thank you, Hannah. So I better get to work. And what do we have here that's different? Ooh, 2 oxygens. Notice there's this carbon, carbon double bond oxygen, carbonyl with an oxygen. On this oxygen, I have carbons, and I'm going to call that R prime. Now my carbonyl carbon, I have carbons to ring, but still carbons, and that I'll call R. And what do I have? Ester. And we're reacting with sodium hydroxide and water. This is saponification of an ester. And what do you get? You get not the carboxylic acid you would have used to make this ester, but the carboxylate anion of the carboxylic acid you would have used to make that ester, plus the alcohol you would have used to make that ester. So if we look over here, what's our? A cyclopentane ring, carbonyl, O minus, Na plus. You don't have to show charges, I will. And the alcohol, oh, 2 carbons. And that's what you get. Now, later this semester, when we get into fats and oils, I'll show you how this reaction can get your drain pipe's clean and unclogged. And we'll go through that. All right, let's try the fun part of organic chemistry. What would you react with sodium hydroxide and water to make those two compounds? Thank you, Jimmy. Thank you, Hannah. Thank you, Jordan. I've been debating, and I think I will. Sometime after the 4th, I'll be sending out emails to everybody and asking about when you're available to meet with Dr. White with your webcam on. Because this is my way just to meet you and not to see whose name's on the screen. All right, let's do this. What are we reacting something with? Sodium hydroxide and water. The first chemical, what's different? Ooh, 2 oxygens, carbonyl and this anion. And this carbon, I'll call R, and we have a carboxylate anion. Then carbon, oxygen, hydrogen. Oh, hydroxycarbon of carbon, I'll call that an alcohol. And what do you react with sodium hydroxide and water to get the carboxylate anion and this alcohol? And the answer is an ester. And this is R methyl. Oh, and R prime is methyl. So let's put it together. R is methyl, carbonyl, carbon double bond oxygen, another oxygen, and my R prime is methyl. And that's how you do. Oh, I got to do one more. I'm having a good time. By the way, let me slow down. Everybody get that or check their answer? All right, let's move on to another one of these. Oop, didn't want to do that. All right. Let me just do something. All right. And the question is, what would be the 2 products that you would get if you react that compound with sodium hydroxide and water? Your turn. Let me just do something quick and I'll bring the screen right back. I had too many things open. There we go. Thank you, Hannah. And thank you, Jimmy and Jordan. So I better get to work. we look at this, oh, we got a benzene ring, but benzene will not react with this, but it's attached to what's different? Carbonyl with an oxygen. If I call the benzene ring R, which I can and I would do, what's on this oxygen? I'll call that R prime. Remember, R and R prime are like X, Y, and Z in math, just variables. And if I react that with sodium hydroxide and water, remember sodium hydroxide is a base. What do we get? Well, we get back the carboxylate anion of the carboxylic acid we would have used to make this ester. And you also get back the alcohol you would have used to make that ester. And now make a little room here. And what's our a benzene ring? So I have that carbonyl, oxygen, and a minus, and a plus. So I've made that carboxylate anion. Then my alcohol, what's our 3 carbons? Which carbon is bonded to this oxygen? The end one, that will be the one that has the hydroxyl group. So 3 carbons. And that's how you do saponification of an ester. Now, we'll learn later that the ester, you can react with sodium hydroxide and water to make this carboxylate. When R is very long, R plus this carbon is 18, we call that soap. But that's only when R is very long. And I'll be teaching you about that. Plus, coming attractions. I'll teach you how you get your hands clean with soap. That's organic chemistry. Same thing if you wash your clothes, your car, whatever. All right, let's move on. Now, the next reaction I love, it's exciting. And that's the reaction of an ester or esters with Grignard reagent, second step, water and acid. And I have a mistake here. I can't do that because from my software. It's not really a mistake for me, but for you it is. So I'm going to correct it right now. If I take an ester, and first step, and here's the mistake for you, not me. At my level, we don't balance anything, but to help students out, I'll put 2. You get acid and water, and you get 2 products. One, and why this is very special, you make not 1, but 2 carbon-carbon single bonds. Very special, very rare, and very good. That's 1, that's 2. And this becomes an alcohol. This carbon is this carbon. Now this right here becomes a second alcohol. And in real life, you could try and keep R prime very small so you can distill it off real quick to get the actual product you're trying to make. Now, what's going on here? Now, Dr. Lloyd's going to have some fun. I will. This will not be on a test, but watch. The first Grignard reagent, by the way, X can be chlorine, bromine, or iodine, attacks the ester and gets you this compound, plus this. And then this one is a ketone. And you learn that if you have a Grignard, second step acid and water, you'll get an alcohol. And the second one attacks too, opens it up, and you'll get this alcohol. Now, this is the conjugate base of an alcohol. And if I add acid and water, which we do in the second step, I'll turn it into this alcohol. And that's how it does it. No, it does it. All right, now take a deep breath, let it out. Take a deep breath. It's a little complex at first, but this one's fun. And here we have some tea, blackberry tea. Oh, is it good? But back to chemistry. Actually, that's chemistry too, but back to this problem. What's different? What's not carbon? What's not hydrogen? Should get your attention. Oh, it's not working today. So get your attention like that did. And that's these two oxygens. And we have a carbonyl, carbon double bond to oxygen. Oxygen here with carbons on it. I'll call that R prime. That these carbons on the carbonyl, I'll call that R. And we have an ester. And what do we have here? Ooh, two of something for Dr. White's class. That's unusual. He balances things. And R group, I'll call that R triple prime. Mg, magnesium X, where X is a halogen, chlorine, or in our case, bromine, or iodine. And you get two products. And I should have put this here, but I forgot. No, I didn't. Second step acid and water, H plus acid, H2O. I hope you all know it's water. And what do you get? Keep your eye on the carbonyl carbon. The R group is attached to it, stays attached to it. Then the R triple prime, not one, but two, bond to this carbon. And this becomes an alcohol. And this right here becomes the second alcohol. So if we come up here, what's R? This. What's R prime? Oops, not that oxygen. Hold on. That's R prime. And then this methyl group is R triple prime. So let's put it together. Keep your eye on the carbonyl carbon. This one becomes this one. So I have carbon. My R group right here is still attached there. Do you break carbon-carbon single bond? No. You can make them though. And now I'll have on that same carbon, not one, but two R groups, triple prime, from the Grignard. This case is methyl. And you get this alcohol, which we see right here. And are we done? No. We get a second alcohol. And what's our prime? Methyl. And we get our second alcohol. Now, when you do this, you try and make R prime small so you can distill it off real quick. And this is the real molecule you're trying to get. Now, as a special July 4th gift from Dr. White, on my test and on my final, this reaction, ester reacting with two molecules of Grignard, second step acid and water, I will never give you a synthesis problem. I'll only ask you to give the product or products. Again, for this reaction, my special July 4th holiday gift to you is I will never give this as a synthesis problem. What's the starting material? But I will ask, give the product or products. Have you noticed here, I have a simple ester. This is a simple ester. I have a simple Grignard, and I've made a very complex alcohol. And that's the beauty of this reaction, which is another reason why Victor Grignard won the Nobel Prize. So it's your turn. And I'll help you out. You get two products. So give the organic product or products for the following reaction. 3 points each. Hi, Boris.
Hi.
And when you're done, give me a thumbs up. But take your time. This is a challenging reaction at first. I shouldn't have said that. I should have said, it's easy as pie, but then I'd be lying. Thank you, Jordan. Thank you, Jimmy. Thank you, Hannah. All right, let's do this. Look what's different. What's not carbon, what's not hydrogen should get your attention like that did. And if we look here, this molecule, ooh, I've got an oxygen here, double bond to this carbon, carbonyl. And I have an oxygen here, and this oxygen has carbons on it. I'll call that R prime. And the carbonyl, carbon double bond oxygen, has these carbons, I'll call those R. And then, ooh, what do I have here? Carbon, ooh, this is different. Magnesium chloride. And that is, and I did it again. Forgot to put the 2 there. At my level, we don't balance it. We don't put a 2 there, but I keep on forgetting. It's one of those reactions I always do. So somebody should have reminded me. We have R triple prime, 2 of them. We have magnesium, and X is a halogen, where X can be, in our case, chlorine. It could have been bromine, or it could have been iodine. And keep your eye on the carbonyl carbon, because that's where the fun is. And second step, acid water, got that. And what are the 2 products? The first product what's attached to the carbonyl carbon is still there, becomes an alcohol. And then from the Grignard, you get the 2R triple prime. And the second molecule from here, remember this is an ester, you get a second alcohol. And as I said, you try and keep the small molecular weight, a few carbons, because that allows you to pull it off with a vacuum easily. Let me give myself some room. Oh, excuse me. And so keep your eye on the carbonyl carbon, which becomes this carbon. It's got a hydroxyl group. The R group is still on there. So that's 2 carbons. And then I'll have my 2 Grignard. And the carbon with the magnesium halide is the carbon bonded to this carbon. Well, it's ethyl, so, and I have not 1, but 2. I know there are 4 bonds to carbon, so I can put in my hydrogens. And then I'm going to get a second molecule, and that's from this, and that's an alcohol. My R prime is CH3, CH2, and OH, and that's how you do it. Oh, I want to do another one, so I will. Remember to put the 2 there? I did. And why don't you try this one? What would be the product if you were, hold on. I forgot something important. Oops. There, unoops. I guess that would be poo. No, it doesn't sound right. Oops, backwards. Oh, I guess it would be soup. Doesn't sound good either. All right. What are the 2 products you would get? I got to cut that out of the video. Nah, nobody will ever see it, except you people. What would be the 2 products you get when you do this reaction? Your turn. Don't forget the hand in labs. There's a lab due today. There was a lab due last Tuesday. Get your labs in. They're easy points. You don't want to lose points because you didn't hand in a lab. That's what makes them easy. Oops. Thank you, Jimmy. Thank you, Jordan. And please be patient. Let's give everybody time to finish. Thank you, Hannah. I'll give Boris a little more time. Thank you, Boris. All right, let's do this. What do I have? What am I starting? Let's look for what's different. What's not carbon? What's not hydrogen? Ooh, oxygen's on the same carbon. Carbonyl, carbon double bonds oxygen to that carbon. Oxygen with carbons on it, I'll call that R prime. And the carbonyl carbon, carbon double bond to oxygen, has carbons, I'll call that R. What do we have? An ester. Now, what are we reacting at? Ooh, two of something. And what do we have here? A benzene ring, but a benzene ring won't react with an ester on its own. But we have carbons, carbon, magnesium halide, and that's a Grignard. And that's where X equals chlorine, bromine, or iodine. And second step, acid and water. Keep your eye on the carbonyl carbon. That's where the fun is. What's attached to it are still, this becomes an alcohol. And now we make not one, but two carbon-carbon single bonds from the Grignard. Then the second part is this alcohol from the OR prime. So let's come up here. What's R? Methyl. What's R prime? Methyl. What's R triple prime? This whole thing here, there's a name which I don't expect you to learn. That's called benzyl. So let me make a little room here. And so this carbon right here is this, becomes this right here. So I'm going to put that there, hydroxyl group. What's R? Methyl. What's R triple prime? A benzene ring with a CH2. By the way, that's called benzyl group, but I'm not going to ask you to learn that. So I'm going to do 1. And then another one, my second R triple prime. All right, that's the first alcohol. And then you'll get a second alcohol where R prime, which in this case is methyl, and OH methanol, which you can pull off easily. It's low molecular weight. But look at what we just made here. From a simple ester, and this is really a simple Grignard reagent to make, we have made this very complex alcohol, very complex, in one step. And that's the beauty of this reaction. You can make very complex molecules quickly and easily. All right, let's move on. Something I haven't talked about, and I should, is when you have a molecule with two functional groups. And I talked about it earlier, but I'll do it again now. If it's separated far enough, each functional group reacts like it's alone and undergoes the same chemistry we've done so far this semester. So let's take a look at that. Let's look at I could have a carboxylic acid, but something that's more reactive. This is called an acid chloride. You saw it in one reaction, but it reacts just like a carboxylic acid, but much more reactive. And then I have ethylene glycol. Now the reaction which you learned already, is this. You take a carboxylic acid, and by the way, instead of OH, if you have a halogen like chlorine, same thing will happen. Alcohol, you make an ester. So this will make an ester. And you don't have to copy this down, but it's something I think you'd like to learn about. Now, if we look at this end, we have an alcohol, which can react with more of that. At this end, we have the acid chloride, which can react more with that. And if I reacted this with more ethylene glycol, this isn't going to react, so I'm just redrawing it. You don't have to write this down. This ester is still going to be here. And it's this oxygen, which is this alcohol. I'll make an ester right here. And if you keep on going, I can react this with more ethylene glycol. Then when I put that on there, it can react with more of the this diacid chloride, which has a name, and that's terephthalic acid or terephthal chloride. Nope, that's not what I wanted. Sorry about that. That's still not what I want. That's what I want. Now, if you react the terephthalic acid and the ethylene glycol, here I have the carboxylic acid, which would make the ester. In real life, you use the acid chloride, terephthal chloride. You'll get a repeating unit that you can put in a bracket. And here's the repeating unit. And notice you have N, and this repeats over and over again, and you have a polyester. And polyesters, poly means many, and ester is the functional group that holds these. Think of it like a long train and the same boxcar connected over and over again. However, on this long train, a molecule, N is about 1 million. Yep, 1 million. And what would we name this? Well, that would be called polyethylene terephthalate. And I'm going to go another 30 seconds and we'll take our break. Hang in there. Polyethylene terephthalate. Polyethylene terephthalate. Wow, that's a thirsty word. Hold on. I need some water. Polyethylene terephthalate. Did I tell you organic chemists are lazy? I need some more water. It's so thirsty saying that. You know something? I don't want to say polyethylene terephthalate. What if I just say part of this name, like the P, the E, and the T? And we'd call that PET. And PET is the polymer, a polyester. And guess what? This bottle is made of that material. If you go to any supermarket and you see any pop, you know, that's the non-alcoholic carbonated material in bottles or cans, it's in a bottle. That bottle is PET. If you look at the bottom, you can see a little thing telling you that. But all our water bottles and pop bottles are made of polyethylene terephthalate. The next time you look at mine or your own or a pop bottle, that's a polyester. Lots of esters to make this. And with that, oh, I went over. Let's take a break and come back at, let me get to my whiteboard. Hold on. No, it's not my whiteboard. 2 days later, I'll find it. There it is. $2.52. We'll start again. I'm going to get up and stretch. I'll see you in 5 minutes. I'm back. All right. Now, let's take a look at where we were. And if you notice, we're at the end of this chapter. Oh, here's a secret. If you look in the lower left-hand corner, since I'm using Microsoft Word, I can do PowerPoint, but this is better for students. We're on page 31 of 31. I'm done with this chapter. And what that means is, listen carefully, on Tuesday, remember, we don't have any class on Monday. I gave you the day off because you've been so nice to me. Remember, it's 4th of July. On Tuesday, I will go through the carboxylic acid and ester problem set. On Tuesday, I'll be going through the carboxylic acid and ester problem set. And don't forget, it's summer, things speed up, we're speeding up, keep up. Do the problem sets, don't wait, don't get behind. I want you all to get a good grade, so do the problem set when it's right before I go over it. And that will help you get a good grade. So next Tuesday, I will go through the carboxylic acid and ester problem set, which means it's, oh, I got to do it again. It's new functional group time, new chapter. I better warn you, Dr. White's going to be very happy because this is one of the other areas I'm an expert in, world authority. And what's that new area? And that's, let me move this out of the way for me. That's chapter 11, 13 mixed together. And that's amines, amides, and heterocyclic compounds. And this chapter, I'll be getting into some stuff you wouldn't think I'd get into, but I will. And why am I so happy? Because amines, amides, and certain derivatives of amines helped pay my house off, got me around the world, got me to Europe a lot, got me to Mexico, got me to Canada, and it got me a number of patents. So this is an area I know quite well. And along with aldehydes and ketones, this is one of my functional group, comfort functional group areas. I like to think about it, makes me feel good. Now, one of the things, and I have to admit it, I'll talk about and show you how I use organic chemistry to help me, is one of the dumber things I've ever done in my life. And boy, was it dumb. But thank goodness I know organic chemistry and helped me out of a bad situation. But we'll talk about that and we'll get into some stuff. Oh, I got a little piece of white there. I am white. I'm a big piece of white. Oh, bad humor Thursday. That was awful. But anyways, I'll talk about that and we'll get into stuff that's really, really hot. And I'll also teach you how to get your clothes nice and soft and how to get your towels working again if they're not absorbing moisture when you use them. So there's a lot to do. Let's get going. Now, what is an amine? An amine is an organic derivative of ammonia. Derivative means made from ammonia. In case you forgot, I'll never ask this on a test. NH3 is ammonia. And what is an amine? That's where you replace one or more of the hydrogens on nitrogen of ammonia with alkyl groups, cycloalkyl, meaning rings, or aryl, meaning benzene rings. And these are what we call amines. Now, here's something important. Nitrogen, unlike carbon, has 5 valence electrons. And normally you say, well, for covalent bonds, I want to have an element with an octet. So if this is 5, how many do you need to get to 8? 3. And therefore, normally nitrogen has 3 covalent bonds to it to complete its octet. So unlike carbon, where there's always 4 bonds to carbon, nitrogen has 3. But let's add something exciting to the mix. And that is these non-bonding electrons right here. Can also be used in a bond. So nitrogen has a lone pair of electrons that can bond. And what that means is you can have 3 bonds to nitrogen or 4. Yeah, it gets a little tricky at times, but unlike carbon, which is always 4 bonds to carbon, in amines and their derivatives, molecules made from amines, you can have 3 bonds to nitrogen or 4. And we'll see how to tell the difference. All right, switches off for this slide, but I'll use this terminology. A primary amine looks like this. And notice we have 3 bonds to nitrogen, 1 from the R group and 2 hydrogens. And that's a primary amine. Sometimes you'll see it written like this. And then you can have a secondary amine, 2 R groups on the nitrogen. And this, sometimes people will write like this, amine, or like I had up here. Most of the time you'll see just the word amine, you won't see a structure. So I'm going to erase that. Oops. Now, a tertiary amine, 3, has 3 R groups on the nitrogen. And finally, my favorite, because this is where I have some patents, and I made a lot of money with this, it's called a quaternary ammonium salt. And I'm going to simplify this. A quaternary ammonium salt has 4 covalent bonds. Now, since the nitrogen is providing both electrons for the 4th bond to R group, it's got a positive charge. All molecules in nature have a net 0 charge, so you need an anion. And for this class, we'll use this to halogen anions. And X here again can be chlorine, bromine, or iodine. Now, Dr. White's going to try and be a good teacher, because if you work with quaternary ammonium salts, organic chemists are lazy. We use slang and we just call them quats. And I'm going to try not ever again, while I'm teaching you this, to use slang and call them what I just said I won't call again. I'll call them quaternary ammonium salts. And this is where I have a number of patents. I should mention that for a number of years, I was section head of research and development for process and product development for all of North America for AXO, then was Chemie, now it's AXO Nobel, nitrogen derivatives, meaning amines and things you make from amines. And it was an amazing job. And part of my job at that level was a manager. I was responsible for developing new products in that product line for our salesmen to sell. I was responsible with people working for me who were working for me, other PhDs, masters and technicians, BS chemists, to solve and come up with new processes to make molecules we needed. And finally, do problem solving. If a customer is having a problem with our product, go to the customer. If our plants are having problems, go to the plant. And in fact, one time I happened to be in AXO when I was there, was headquartered out of the Netherlands, which is why I went to the Netherlands a lot. And I happened to be there for a couple of weeks. I'd been there a week or so. And the vice president of manufacturing, who was located there, called me up. I was in Deventer, which is a town in the Netherlands, staying there, working with people, and said, are you doing anything tomorrow? I said, yeah, but it can be changed. He said, good. I'm going to have one of our people drive you to France. You'll leave tonight. You'll stay in Belgium. And the next day you'll go to our plant in France. They're having problems. We really want you to solve it. So I went to Belgium and stayed with the sales rep who was driving me. It was his area, so he knew the territory, how to get from Deventer to the city in France I went to. I can't remember that name. And we stayed in the capital of Belgium, Brussels. And quick little Dr. White story, I got time. One of my mother's brothers, my uncle, was in World War II. My father was a pharmacist, and because that was an important occupation, he was never drafted. And this one uncle was in the Battle of the Bulge. It's one of the worst battles of World War II, and very, very tough battle. And Uncle Joey, who's long gone, unfortunately now, when he came back from the war, stuttered. When I knew him, he stuttered. And he never talked about what happened. But when he came back, the only thing he brought for my mother, my mother's brother, and his parents, my grandparents, were these little statues of a fountain in Brussels. And it's called the Mannequin Piss. And it's a statue of a little boy doing, you know what, and you know where the water's coming out. Look it up on Google. And I had been talking a couple of times before when I'd been in the Netherlands, you know, someday maybe I could see that. And I said, well, all right, maybe if you ever get to Brussels. And somebody told that salesman, we were in a nice hotel, and he said, let's walk to the restaurant. It's a nice night out. And it was, I think, September or October, and it was beautiful out. And we went, we were going through the old part of Brussels, and he's saying, look at all these beautiful things. And he said, I got a surprise for you. He said, next corner is your surprise. I said, what are you going to do? I'm not going to tell you, it's a surprise. We turned the corner, and there's the original fountain Mannequin Piss. And all around there are souvenir shops, which had brass like the ones my uncle brought home, up to ones that were bigger than the actual statue. And there's this little boy on a pedestal, and you know where the water was coming out of. That's my one AXO story. But let's get back to amines. So, how do you name amines? Well, good news. Most of us never in the business use IUPAC names. And I can tell you that, but I'm not going to. Now, for amines, you name the alkyl groups or cycloalkyl groups or aryl attached to the nitrogen. Well, I'm missing stuff here. All right, how do you name common name for amines? You name the alkyl group or alkyl groups on the nitrogen as alkyl groups, like methyl, ethyl, etc., and then add the word amine at the end. So let's take a look at one or two examples. remember, there's 3 bonds to nitrogen amines. So if we look at this, what's on the night? First of all, look for what's different, what's not carbon, what's not hydrogen. Should get your attention like, oh, let's use a different one. That did. And we have a nitrogen. And it's got carbons, our group, and 2 hydrogens. And this is an amine. It's a primary amine, but I won't ask you to do that. Just you should know that's an amine. And how do we name that? Well, the alkyl group is methyl. So this is called methyl amine. Now, something I have to show you, which we haven't done with carbon, but you can do with nitrogen. Let's look at this molecule. And what would you say it is? Ooh, nitrogen with not 1, but 2 alkyl groups. That's an amine, secondary amine. Notice they're both methyls. How do we say 2 in organic? Di. So that's dimethylamine. Now watch closely, because I'll do this on a test, and in real life, organic chemists do it. You can write dimethylamine this way, but notice on the nitrogen, we have 2 methyl groups. So being a lazy organic chemist, I'll put the methyl group in a bracket, number 2, and this is also dimethylamine. This says there are 2 methyl groups on the nitrogen, and you could draw it this way or this way right here. And 9 times out of 10, I'm going to be lazy and I'll draw it this way, including on its S. And you should know the difference. Now, if you want to draw things this way, if I ask you to draw molecules, that's okay. Or you could do it this way. All right, let's continue on. And if you notice on the nitrogen, there are no hydrogens. Why not? Because in an amine, there's 3 bonds to nitrogen, and this already has its 3 bonds. So how would you name that? And I'm going to give you something to try in your own too, but I want to go through this. Well, what are the different R groups? And again, look for what's different. Nitrogen, I have this R group, this, and this. And since this is common, there's no rule which goes first. So I'll do T-butyl, ethyl, methyl, amine. And that's one way, the common way of doing that. Now, your turn to have some fun. And why don't you name that molecule? What's the common name? And on test 3, unlike test 1 and 2, the nomenclature problems will be give the IUPAC or the common name, because for amines, I'm only teaching you common names. I know the IUPAC, but we never use it. And trust me, I worked in this industry and I still consult in it. We don't use IUPAC names. And when you're done, give me a thumbs up. Remember, name the alkyl group and put the word amine at the end. Thank you, Jimmy. Thank you, Hannah. Thank you, Boris. And please be patient. I like to give everybody time to finish. All right, let's move forward. Now, when you look at a molecule, look for what's different. What's not carbon, what's not hydrogen. Ooh, nitrogen with carbons on it. This is a primary amine. I don't ask you to name it that, but for any amine, how do you name it? Look at the alkyl groups, the R group. What is this? N-propyl. And then it's primary amine. I'm done with the alkyl groups, and I'll add the word amine. And that's N-propylamine. And we're getting in stuff I can talk about. Say hello to my old friend, this molecule. I used that molecule in graduate school, even before I worked for AXO. What would be the common name for that molecule? Hi, Janet. Hi, Janet.
Hello.
I saw a real person, not just a name. Oh, am I happy? I don't know what it is. I won't let you see me anymore either. No. I don't know what it is. When we first started doing Zoom, students would turn on their camera. Then over the last year or so, students stopped turning on their cameras. Happened last semester too. I think I had one person who turned it on. But that's your choice. For those who came in late, after today's lab, within about 5 to 7 minutes, I will send out 5 to 10 minutes. I will send out an email with the password for test number 2. You'll have until tomorrow, 11 a.m. to take test number 2 and upload your answers for test number 2 as a single PDF file to D2L. And excuse me, take about an hour and a half. You should only need about 40, 45 minutes to actually do the test. And don't count in that hour and a half the time it takes you to either take a picture or scan the test and upload it. That's separate. Just have it done by 11 tomorrow. All right. I don't know if anybody did a thumbs up, but I'll do a poll. Time to vote. Hopefully you all voted on Tuesday. I did. It's important to vote in the primaries because that's when you have a choice to keep certain people out and certain people anyways. And we're doing amines. You name the alkyl groups on the nitrogen and add the word as alkyl groups, and then add the word amine. I'll only ask comment. All right, let's do this. What's different? What's not carbon? Ooh, or hydrogen or nitrogen. I've got carbons here, 2 of them. 2, what kind of group? Isopropyl. 2, how do we say in organic chemistry? Di-isopropyl amine. And let's do another one. And here's one more for you to do. And the question is, what's the common name for that molecule? 3 points each. And to be on the polite side, instead of asking you to do a thumbs up, I'll send out the poll. So you can vote. Are you done yet? All right, let's do this. And the question is, what's the common name for this molecule? And if we look at this, we have, oh, look, a nitrogen and 3 alkyl groups on it. That's a tertiary amine. I'll never ask it, but let me just say it's an amine. And how do we identify the common name for an amine? name the alkyl groups on the nitrogen, and then add the word amine. And what do I have here? Oh, it's your old friend, the methyl group. But there are two of them. How do we say two? Dimethyl. And then two carbons, ethyl, amine. Now you could have also, which is correct, because there's no rules for order for common names, ethyl dimethyl, amine. And that's how you do it for amines. Oh, but let's go the other way. How do you draw something? And let's try this. Why don't you draw methyl T-butylamine? Your turn. While you're doing that, let me check something quickly. Nope, I forgot to put it in the slide. I'll do it on the screen. All right, let's get going. Now, how do you decode this? Well, all organic compounds, you start from the right, move left. Ooh, an amine. That means a nitrogen compound. And this is a common name. So I have what's on nitrogen, T-butyl and methyl. Doesn't matter which side you put it on. You can put the T-butyl here. You could put it on any of the four sides. And then I'm going to have a methyl. Now, in amines, how many bonds to nitrogen? Almost said carbon. That's a mistake I made. And the answer is 3. Notice I have 1, 2. 3 minus 2 equals 1, meaning I also have to put a hydrogen. And that's how you draw it. Oh, let's do one more. And here's your one more. Draw the structure for isopropylamine. All right, let's go forward. How do you decode this to know what to write? You start from the right, move left. Amine. And it can be like this, where any amine, R prime, and R double prime, one, both, or none, can be hydrogen. Well, in this case, I have a nitrogen. That's what this amine tells me. It's got a W. Hold on. I have a nitrogen. That looks better. And what's on there? An isopropyl group. 3 carbons, the center carbon bonded to the nitrogen. Now, how many bonds to nitrogen? 3. I have 1. 3 minus 1 equals 2. So I have 2 hydrogens on there, and that would be isopropylamine. Now, I noticed I didn't have a slide for it. I'll try and do one and send it out to you over the holiday break. But let's talk about my favorite amine derivative, and it's made from amine. Quaternary ammonium salts. And that's where you have a nitrogen with 4 groups attached to it. They can be the same or different, which is why I do R prime, R double prime, R triple prime. That's like WXYZ in math. And this has a positive charge, and they're different anions, but for this class, we'll say the halogen anions, and that's X can be, for my class, chlorine, bromine, or iodine. You could actually have fluorine, but I've never seen it. It's only in certain very rare academic issues do you see fluorine. Now, how do you name this? And this is the common name, not the IUPAC. Nobody uses IUPAC. Hang in there. I got a lot to write. All right. When you name quaternary ammonium salts, you name each of the R groups in front as the alkyl group it is, just like we did with amines. But at the end, instead of putting the word amine, you put ammonium halide. Now, the halide part, if it's chlorine, is Cl minus. That's chloride. Br minus, bromide, I minus, iodide. Again, name each R group as the alkyl group it is. Then at the end, add ammonium halide. If the X minus is chloride, Cl minus, and halide is chloride. If it's Br minus, it's bromide. And if it's I minus, it's iodide. Now, in reality, this chloride is bonded to this nitrogen by what we call an ionic bond, but we usually put it where I am, put it to the right here. Now, let's take a look at this molecule. How do you name the common name? Well, it's got two methyls and two ethyls. It doesn't matter which you put first because it's a common name. Diethyl, dimethyl. How do you know di? It's in a bracket with a number on the side there. Next, we put the word, because this is a quaternary ammonium salt with 4 groups, 2 plus 2 on the nitrogen, ammonium. And next, we have the anion, and Cl minus, oh, someone's nice to write on our screen, is chloride. And we have dimethyl, dimethyl, ammonium chloride. And that's what this is. So you name the alkyl groups as alkyl groups. And if there are 2 of them, di, 3 is tri. Remember. And let's have you try one. And here's the molecule. Now I'm going to help you out. Br minus, what is that called? Bromide. And remember, name each of the alkyl groups and then the word ammonium, in this case, bromide, the halide. Now, just remember, di is 2 groups, tri 3 groups. Di 2 groups, tri 3 groups. And here you are. Ooh, I got a surprise for you. After the break, I haven't done this all semester yet, but I'll do a couple now next week or 2. I'm going to have Dr. White's show and tell. When I was in grade school, teachers were really afraid when we have show and tell what I would do. And the reason they're afraid is I talk about something they had no idea what I was talking about. I remember once in I think 6th or 7th grade, I gave a show and tell and talk on plain polarized light, and the English teacher had no idea what I was talking about at all. She wasn't happy either. But I said, hey, you said anything you wanted to bring in and talk about. Even then, I knew I was going to be a chemist and a scientist. All right, it's almost time for the break, so I'm gonna go to it. Now, how do you know how to name this? You look what's different. Nitrogen. Ooh, it's got a plus charge. You got an anion. It has 3 + 1 equals 4 groups on it. That's a quaternary ammonium salt. So notice I have CH3 methyl 3, that's trimethyl. N-propyl, and it can be any order. You could put the N-propyl first. Ammonium, because that's what you put for a quaternary ammonium salt. And then Br- is bromide. I knew it, but I wanted you to see it so you know it. And with that, it's time for our break. Remember, when we come back, I'll have a surprise show and tell. Really. And with that, let's take a 5-minute break. Come back at 3:50. And I'll see you in 5 minutes. Be with you in a second. All right. Sorry about the delay. Now it's show and tell time from Dr. White. Now, I said the first day he'd learn personal things about me. Unfortunately, one personal thing, which is hereditary, is bad dental problems. Inherited from both my mother and father, who inherited from their parents. But anyways, years ago, I had this great dentist. And right now, I have a great dentist too. I've had a couple, but this one, who the one years ago, unfortunately, had heart problems, had to retire, and finally, he unfortunately passed away. And Dr. Rudnick was a great dentist. In fact, he was one of the top dentists in the United States. People came to him from New York and Washington for him to work on their teeth. He's that good. But anyways, I had this gum problem. I touched like that, I'd be in pain. And I had this gum disease that had to be controlled. And I got this prescription mouthwash that you'd use once a day, and it controlled it. Because if I didn't, I'd be in pain right now. Well, anyways, when he retired and I hadn't found a new dentist yet, well, I did, and I didn't like him. I was in between. All of a sudden, my gums are hurting. So I figure, all right, I'm almost out of that stuff, and it's expensive too. For every month, it was about, back then, $50 a bottle. That's expensive. And so I said, you're an organic chemist. So I went to Walmart, and you go where the mouthwashes are, there's a whole wall of them. And there's two types. One is the scope type, and the other is Listerine. And Walmart has their equivalents, which is quite good. They have put pretty, and those type of products, they make good products. I know, I've used them. So anyways, I look at the label for Listerine, and it's a phenolic compound. And since I know organic chemistry and applications, this is the main molecule, I forgot what R is, in Listerine. And phenolic compounds, molecules with phenol, have antimicrobial properties. Well, I bought some. Guess what? Didn't do anything. My gums still hurt. So I went back and looked at the labels again. And the other type of mouthwash is Scope. And Scope has a quaternary ammonium salt. Now, this is a little sophisticated, and I'll teach you more what this means. This is called a pyridine ring. And this is 16 carbons called cetyl. That's a common name. And it's called cetylpyridinium chloride. But it's a quaternary ammonium salt. And certain quaternary ammonium salts have very good antimicrobial, antibacterial properties. And for oral problems, that's why they put it in the mouthwash. So I bought some, and it worked. It still works. See, it works. And if you look at the label, you'll see right there, I don't know if you can see it, cetylpyridinium chloride. And that's the quaternary ammonium salt in this stuff that makes my gums healthy. Because if they weren't, I'd be screaming now. Ouch! Nope, no scream. It works. So, why are you learning about this stuff? It's in stuff you use every day. Now, let's talk about another quaternary ammonium salt, then we got to do our lab. And that's this molecule. And I'll draw it this way. And this is called a tallow group. R sub T. It has 18, 16, a mixture of 16 and 18 carbons. Some have a double bond, some don't. And I'll teach you when we get into fats and oils where tallow comes from and that tallow group. And this would be called ditallow, dimethyl, and you should know this. Hint. Ammonium, it's a quaternary ammonium salt, chloride. Until about 10, 15 years ago, this was the only molecule used for, are you ready for this? Fabric softeners. And when I was at AXO, we were one of the world's largest suppliers of dimethyl ammonium chloride. And that was an area I was responsible for in terms of making it and any problems that we had with it. Now, since I worked in the industry, our two largest customers for this were Procter & Gamble for Downy and Unilever, also back then called Lever Brothers, for Snuggle. And those are fabric softeners. Now, I'll teach you when we get into fats and oils how you get your fabric nice and soft. And also they provide anti-static properties so it doesn't bunch up and cling in the winter. Now, here's a little Dr. White help. If you ever have either dish towels or bath towels, you know, and you, oh, it's not absorbing water that well. And the reason it is, you've got too much fabric softener on there. How do you make those older towels and dish towels work nicely again? You wash it once or twice. When you throw it in your dryer or in your washing machine, you don't use a fabric softener. Then after that, they'll absorb water just like they were brand new. You're taking some of the quaternary ammonium salt that's blocking what's called hydrogen bonding, how a towel absorbs water. And by washing it without a fabric softener, which is a quaternary ammonium salt, that you should know fabric softeners are quaternary ammonium salts, then it works better. Now, having worked with P&G, Procter & Gamble people, and also Unilever people, I learned one thing from them, and that is the dryer sheets work much better softening your clothes than putting the liquid or whatever, the gel, into your washing machine in the rinse cycle. Again, using the sheets is much better than putting it in your washing machine. And with that, I got some more stories, but I'll have to wait until next week because we've got to do our lab. If you notice, I'm having a good time. Dr. White loves quaternary ammonium salt. Almost said the slang, but I didn't. And let's do our lab. And it's lab time. First of all, I got to open it up. Hang in there. All right, let me close this. All right, everybody see on their screen, carboxylic acid lab? Thumbs up, people. Thank you, Jimmy. All right, what's a carboxylic acid? Carbonyl, hydroxyl group, R group. Thank you, Jordan. And this is a carboxylic acid. Now, the hydroxyl group here can hydrogen bond to water, which helps make it soluble in water, unless you look at the size of R. And when R, a lot of carbons, that might overrule, stop the solubility even with hydrogen bonding. Now, is that possible? I'm not going to give away the secret. In part one, you're going to look at the solubility of different carboxylic acids. And what you would do if we were in the lab, you'd fill them about halfway with water, then you put some of the small amount of the carboxylic acid in there, and you'd mix it. Remember, never ever shake a test tube like this. Hold it in one hand, 1, 2, 3, 4, 5. Don't tickle it, really hit it. Or we have in our lab at ECC what's called vibro mixers. There's a motor, you see a rubber disc, you have ways of controlling how fast it does it, and you push down and this starts vibrating and it mixes your test tube content real good, and students love it, and I love it too. But since you're not going to do that in your house, you don't have a vibro mixer of these products, let's look at it. Now, you'll be using acetic acid, propanoic acid, and stearic acid and oleic. Stearic and oleic acid are common names. You can find the structures using Google or your favorite search engine. And if you notice, acetic acid is soluble, propanoic acid, soluble. Ooh, stearic acid, insoluble. Oleic acid, insoluble. And that's the first part. Now, the second part is carboxylic acids reacting with sodium bicarbonate. And this is one of those parts where I tell students if we're face to face, you find out if I'm lying to you or not. Now, this is a carboxylic acid. And as you learn, in case you haven't gone back and had a chance to look at it because you've been studying for test number 2, I'll be sending out the password when we're done with the lab. And you have carbon dioxide, baking powder, sodium bicarbonate, and this part of this lab, we're using some very dangerous chemicals. And when you react it, if you have a carboxylic acid, you'll get the carboxylate anion plus water plus carbon dioxide given off as a gas. Now, this is an acid. If I can spell it, let's try it again. This is a base. And you're making a salt right here. And what happens when you add a base to acid? Let's talk about pH. pH, I think you all learned there's a pH scale. pH is a measure of the minus the log of the hydronium ion concentration, H3O+. But if you have an acid in water or acid, you can measure the pH. Now, if it's acidic and an acid is really acidic and is neutralized, reacting with a weak base, the pH should go up, increase. And you'll find out if you are doing this. Now, what are the products you test? Acetic acid which is really, we use vinegar. Remember, acetic acid and water is vinegar. Then lemon juice, which has an acid in there, carboxylic acid. Same thing with tomato paste. This is dangerous stuff. And stearic and oleic acid. And what we do, and we do this in a beaker because it's easier to clean out. In a beaker, put about a third of water, put in the material that you're testing, a small amount, and then mix it so it's soluble. You measure the pH with pH paper. If you're not familiar with pH paper changes color at different pHs. Let's see if I can find. All right, everybody see Hydron pH paper on your screen right now? Maybe you don't. Hold on. Yes, you should. All right, do you see that? pH paper. Thank you, Jimmy. And what you do is a roll of paper right here, and you take, it's got a foil around it. It's a little long strip, and you take a small piece, and you take a stirring rod, put it in the beaker, take it out, and put a drop on there. And you'll look at the paper, and depending on what color it is, that's the pH of that solution. And if it's, say, real red, it could be 0 or 1, almost this dark blue, 12 or 13. And different colors, different pH. And that's what you would do for the slab. And I've given you. Now, initially, before you add the bicarbonate, here's the pH of different solutions. And when you add a bunch afterward, here's the pH afterward. And when you observe that in the beaker, you see bubbles. Now, I have a couple of YouTube videos you should watch. And the second one, start at 311, watch it for a little while. Do that on your own. All right, now the last one, we're really not doing the stearic, just in the lab now, we do acetic and oleic acid. Now, what you do first is, in an Erlenmeyer flask, this helps you mix it easier. You put some water, then you put a small amount of the carboxylic acid and a phenolphthalein indicator. This changes color. When it's acidic, it's clear. When it's basic, it turns a reddish purple color. My sisters are yelling at me. You don't know your colors. I know my red, green, and blue, but sort of a wine color, purplish color. And what you do is observe the solution. And what you're going to be doing is adding a base to each of these acids. Now, the first one, I'm going to show you the general reaction, and then you need to do the specific reactions. And what you'll do is take the acid, either acetic or oleic, and add some sodium hydroxide. And that does this reaction, which I'll show you in a second. And then second step, you'll add to the cis solution right here, some magnesium sulfate solution. And observe. And you can see it in this video, but let me get to the whiteboard. Take notes or come back and watch this video. Now, if you have a carboxylic acid and you add sodium hydroxide and you're in water, classic acid-base reaction. And this is reaction number 1, and you should know this. And you get the carboxylate anion plus water. Now, reaction number 2, which I'll balance, which is rare for Dr. White, you take 2 of the carboxylate anions, it's in the beaker, and you add some magnesium sulfate solution. And what happens is, this is really Mg plus 2 and SO4 minus 2 ionic compound. And when this happens, you get a cation transfer. This carboxylate becomes this carboxylate. Why? 2, because all molecules have a net 0 charge. This is a plus 2. Is only a minus 1 to get to 0. You need 2 of them. And you also make this, which is water soluble, sodium sulfate. Now, depending on how big R is, notice from here to here, you doubled the molecular weight approximately. And how does that affect solubility? If we go back, you'll see for the acetic acid, when you react it with base, it's clear, homogeneous solution, same throughout. And when you react it now with the magnesium sulfate solution, it's still clear and homogeneous. But the oleic acid is larger. You got to look up how many carbons. With base, you get a clear, homogeneous solution. When you add now the magnesium sulfate, you get a white solid. And you'll see that in this video. Now, if we were in the lab together and you're working on doing that, and you go like this with your Erlenmeyer, you see this white goop and solid, the liquid, and covering the glass all around inside. And I'll say, you know what you just made? And students say, no. I said, you've just done the same type of reaction that makes the bathtub scum in your bathtub or shower. And there, instead of magnesium plus 2 in your water, Chicago water has it, not as much as other places, you have calcium plus 2. And that dicarboxylate calcium salt is the bathtub scum if you use bar soap in your bathtub. And I tell students, you just made bathtub scum. They look at me like, oh, okay. But that's what you did. Let's go back to the lab. And there are the questions at the end. Now, let me point out something important. Look at part 3 question right here. You need 4 experiments for each of the 4 experiments with sodium hydroxide for each one, carboxylic acid, and for the follow-up magnesium. 4. Let's go back to my whiteboard. Here are my 2 reactions. And you have to do that by putting R here as acetic acid. And same thing here. And then a second time where R and this is oleic acid. And those are the 4 reactions you need to write. This one here where R is acetic, this one here where R is acetic, and the second one, this one here where R is oleic, and this one where R is oleic. Those are your 4. Don't forget to do that or I take off points, which you shouldn't have that happen. And with that, because it's a holiday weekend, remember, we won't have any class on Monday. We can stop by, but I'm not going to be here. I'll probably be at my best friend's house for our 4th of July picnic at his house. But with that, I'm going to wish you a happy 4th of July weekend. In a couple minutes, I will be sending out the password for test number 2. You have until 11 tomorrow morning to take the test and upload it. And with that, I'm going to say, Gang gesund. Goodbye.